Hi everyone. In this video, I'm going to present one of my graduate projects that I have done for my Broadband Network class. It was on the simulation of MPLS LDP using GNS3 software. So here's what we're going to do. First, I'm going to talk about the goal of this project. Then I'm going to introduce the concept of MPLS and LDP, followed by the lab tools and setup for my project, and then I will briefly go over the steps and results of this project. So the goal of this project was to implement MPLS LDP, which is multi-protocol label switching. Label distribution protocol is LDP, using GNS3 simulation software. Implementation of MPLS network is a very important concept in today's high-speed broadband communication world. In this project, this protocol was implemented using CISCO configured routers. So let's talk about what MPLS protocol is. In this protocol, data packets are routed using simple numeric labels instead of long, complex IP addresses. And when entering a tunnel, each data packet gets encapsulated with a label header. And the packet gets routed entirely based on this label from one LSR or label switch router to the other LSR. And packets get labeled again before moving to the next LSR, meaning that each label has only a local meaning, used only between two LSRs. So here's the process of MPLS. At first, each LSR gets updated by OSPF packets and RIP packets about the incoming traffic and neighboring LSRs. Next, each ingress or incoming LSR determines a specific path for a packet from ingress node to the egress node, which is the leaving node, based on the link cost or bandwidth available, or both. And then the next step is to form a forwarding table for MPLS packets using labels. And for this, MPLS can use different protocols like LDP or Border Gateway Protocol or the Resource Reservation Protocol. For this project, I have implemented LDP, which I'm going to talk about next. So what is LDP? LDP is a protocol that automatically generates and exchanges labels between routers, and each router will locally generate labels for its prefixes and then will then advertise the label values to its neighbors. So the LDP process starts with an incoming LSR forming a specific path with respect to the destination, and next the incoming LSR requests a label from the next LSR in the path. It receives a suggestion, and then there is an agreement between the two LSRs, and then after that the forwarding table is created. And as we can see here, LSR1 is requesting a label from LSR2, and LSR2 is suggesting 6, and then there is an agreement between these two LSRs, and this is how the binding is done. And the binding process is repeated between every two LSRs of the specific path, so each time there is a different label. So this is how packets get forwarded in MPLS networks solely based on label values without using any IP addresses. So here are some of the many benefits of MPLS. I'm not going to go into detail, but the most important one is the reduced delay benefits. It is because we're not using complex IP address tables and all that. We're only using labels. It reduces the delay to a great extent. It has improved scalability, and because of the encapsulation that I showed before, data security and integrity is ensured in this process. And since all the routes are predetermined and there are backup routes to every packet path, these MPLS networks are predictable and reliable as well. And then the implementation cost is lower than other broadband communication processes. And also, MPLS has special quality of service features, for example, prioritizing packets and giving some preferred packets more bandwidth and so on. So now let's get into the project that I did. These are the lab tools, the VMware workstation, the GNS3 software, and of course the CISCO 3640 iOS. So at first, 4 routers that already have configured OSPF, or Open Shortest Path First, in them were loaded and further configured in a new project on GNS3. The green lights here mean that they were configured properly and they're functioning properly. And then the routers are named from P1 through P4 as shown here. And now that we have all our routers configured, we can start implementing an MPLS network on them. So to activate MPLS, the first step, routers P2, P3, and P4 were configured using the command MPLS IP as shown here. This command configures MPLS hop-by-hop forwarding globally. However, globally enabling MPLS forwarding does not enable it on all router interfaces. MPLS forwarding on the interfaces have to be manually enabled, and this has been done for P2, P3, and P4. And then the next step, all the routers were configured for an MPLS label range of 20 to 200 as shown here with this command. This means that labels assigned would start from 20 and the last one would be 200. And just as a trick, if you want to check what is the range of labels that can be used for MPLS, you can use this command and it will show you the range of numbers that you can set. The objective of this step was to use the IP address on interface F0/0 of router P1 as the MPLS router ID. And for this, the MPLS router ID command was used, as you can see here, which allows to establish the IP address on an interface as the LDP router ID. And the command MPLS LDP router ID fast Ethernet, as shown here, was implemented on router P1, and it showed the number of interfaces it has. The interface to configure was F00, as you can see here, on which the router P2 is connected to P1. And to forcibly change the LDP router ID, the command, this command with force in it, was used. Before exchanging label information, LDP has to establish neighbor adjacency. And to do this, routers multicast hello messages to a well-known UDP port in order to discover neighbors. Within these hello packets, they will advertise a transport IP address, which is then used to establish a TCP connection between two routers. Once a discovery is accomplished, a TCP connection is established and the LDP session begins. And this TCP connection is then used to exchange label information. So in this step, I have used this LDP discovery command, as shown here, to send the MPLS hello message every 2 seconds and with a hold time of 10 seconds. So this step is to connect the routers P3 and P4 by establishing an LDP connection between their fast Ethernet interfaces. I'm not going to go into too much detail here. There were several steps here. But the command LDP discovery transport address interface is shown here was used in the routers to configure it for LDP, and this is done for the interface F1/0 for both the routers P3 and P4. So in this step, for the data integrity, authentication is used by configuring the routers with a password vault, and this is achieved by using MD5 authentication, which, as we know, is a widely used hash function for data integrity. So this was done in this step. And in this step, TTL, or time to live, from IP packets was copied into the label on all routers. The label part of the MPLS packet header actually has an 8-bit TTL or portion, which serves as a hop counter. At every routed hop, the TTL is decremented by 1. And then if the TTL reaches 0 before the packet reaches its destination, the packet is discarded. So for this, the command MPLS IP propagate TTL was used to copy the TTL into the label of all routers, as shown here. Lastly, so the first task done in this step was to advertise a default route on the router P2. And next, the forwarding table for all the routers were updated accordingly, according to the advertised route. So I'm going to show a little video here. As you can see, the first step here would be to use the show IP route command, which will advertise the route showed on P2. And then what I've done here is, I'm just checking all the forwarding tables by using the just showing the MPLS, the forwarding tables for now. And then finally, I have used the MPLS IP default route command right here. I'm going to pause it so that you can see it. Show MPLS forwarding table, and then here, MPLS IP default route. This command is going to update all the forwarding tables of the routers according to the route shown by P2. So what I'm just doing is I'm using the same command, MPLS IP default route, to update all the forwarding tables for all the routers, P1 through P4. And then finally, when I check the MPLS forwarding tables by using show MPLS forwarding table, I see that there are new entries for each table, which I will be discussing in the results section next. So here are the updated forwarding tables, where we can see that a new route is updated for each router with respect to router P2. So for router P1, there's only one new entry here. And for R4 or P4 also, there is only one new entry. But for P3, we can see that there are two new entries. And the reason for two new entries is, you can see in the picture that to P3 can go to P2 in two ways, through P4 or P1. That's why there are two new entries for P3. So overall, this project was very helpful to understand the concept of MPLS networks in depth. Also, I learned how to use Cisco iOS by playing around with the command line interface in every step. Furthermore, implementing MPLS network using Cisco router is a real-life application, which is implemented in numerous broadband networks every day, and therefore it was a very practical project as well. So I had a lot of fun sharing this project with you, and thank you for watching.